Hi, welcome back. So in this chapter, we're going to talk about selected topics in mass spectrometry, MS in short, and the reference for this part is by Ekman. There's an ebook at the library. It's titled Mass Spectrometry, Instrumentation, Interpretation, and Applications. So feel free to read up more if you want more details. Now for this module, Advanced Analytical Chemistry under the Mass Spec Part 1, we're going to speak about the principles of mass spec and ionization methods. So here are a few questions at the end of this module. In this lecture, you'll be able to answer them. Number one is how to determine the resolution in mass spectrometry. Take note, mass spectrometry, not scopy. What is EI, electron ionization? What is CI, chemical ionization? Why is soft ionization used and useful? And what is MALDI? Now, first of all, we look at how it came about. In Nobel Prize in Chemistry 2002, two professors, researchers, John B. Fan and Koichi Tanaka from Japan, they were awarded for the development of methods in identification and structural analysis of biological macromolecules, for instance, the proteins, and for the development of soft desorption ionization methods for mass spectrometric analysis of biological macromolecules. Now, let's do a short introduction. So, mass spectrometer uses the difference in the mass to charge ratio, or the MZ value, of the ionized atoms or the molecules to separate them from each other, which means to say that the mass spectrometer only detects charged particles. So here we're saying that when you have atoms or molecules and they get ionized, then you can detect them. Now, mass spectrometry is therefore very useful for the quantification of atoms or molecules and also to determine the chemical structure of a molecule. With this structural information, how do we come about it? We look at the information from its fragmentations, right, to piece them together like a jigsaw puzzle so that we have the whole picture. And that allows us to identify the structure. So in just a simple layout here, what happens is, right, your sample goes in, right, via the sample inlet, coming from a source, right, and then we generate ions in the gas phase because remember, if it's not charged, the mass spectrometer cannot detect it. So how to make it charged? We need to ionize it, and there's various modes of ionization, and after they are ionized, we're going to separate the ions based on the difference in the MZ value using a mass analyzer, right? We're going to accelerate them and then detect them, okay, and then transduce them to see on the graph. This is a periodic table, and you can see it's not updated yet. We can look at the IUPAC website for the latest one. It was just revised a couple of months ago. Now, different elements can be uniquely identified by the masses because every element have the isotopic masses, and when we put them on the same charge, right? Let's say it's a single positive or 2 plus, when we divide by the AR, you can have a unique value. So for instance, mass spec can also determine the difference in the structural compounds and molecules, right, by doing different slicing, different fragmentation of the bonds. In this case, your butyrophenol, L-dopa, ethanol here, right? Because if you do not even cut the individual bonds, right, you just take as face value and with a charge there, the molecular weight is 327.1 for this molecule. For L-dopa is 197.2, ethanol is 46.1 here. So you're able to see, right, the mass over charge is a particular value, then can determine the different signals. Now, for smaller organic molecules, right, this molecular weight can be determined within like 5 parts per million, or we can convert into 0.0005%, which is enough to confirm the structure of this mass alone. Remember, 1 dalton is 1 atomic mass unit, AMU in short. Now, for larger biomolecules like proteins, even large DNA, right, this molecular weight can be determined only within an accuracy of 0.01%, right, which means within 5 dalton or 50 kilodalton protein. You need to know the difference is that for large biomolecules, why the accuracy is a bit lower, right? It's not so precise as a small molecule because when you have a large, big piece, right, you can have so many different permutations of ways to fragment them, and so it's no longer accurate to piece them together. So what I'm saying is, right, if you have a picture and you cut into smaller pieces, there could be two jigsaw puzzles that could be the same, that can fit in more than one location, which means there's a chance that you might piece them not so correctly, not the real picture, which means there's a big room for error. But if you cut them into smaller pieces and if the picture is smaller, then the room for this kind of calculations could be smaller. So bigger molecules in general have more kinds of atoms, there's more isotopes and combinations, and therefore less accurate. Now, to be the very simple kind of functions of mass spec principle is sample goes in, ionize them, make it charged, normally it's positive charge, then you analyze it, okay, and then you detect it. So these are a few typical mass spectrometer you see in the laboratory, either in your research lab, graduate studies, or when you work in the industry. So short form, GCMS, right, gas chromatography, in tandem with the mass spec, LCMS, liquid chromatography, a portable mass spectrometry, ICP-MS, right, you have your inductively coupled plasma, mass spectrometry, FTMS stands for your Fourier transform, ion cyclotron resonance mass spectrometry. So sometimes people can call it your FT or ICR-MS, but in short, you can just say it's FTMS. LC, MSMS, so it's LC square, MS square. So it's a tandem liquid chromatography and tandem MS. So we got MSMS, in the lab, we call MS2, MS square, LC. So we have a tandem. Now for typical mass spectrum, okay, spectrum just one single spectrum, plural spectra, you have these characterizations by very sharp narrow peaks. Even you can see it's like lines, right, because they're so sharp. So the x-axis, the horizontal axis, indicates the MZ ratio, mass over charge ratio of a given ion. So we normally take it with the assumption it's a singly charged ion. In this case, so its bottom is 1, right? And the height of the peak, right, the height of the peak indicates the relative abundance of an ion. So it's relative because you see many of these vertical lines, right, peaks. So it's about relative to the other peaks. So it does not give you how much of the sample you have here. So therefore, it's not very good in general to look at it as a quantification method. That means to determine the concentration of a sample, because you just slice them apart. Now, the peak intensity, right, if it's very high peak, it indicates the ion's ability to desorb, to escape from the analyzer, to fly, right? And of course, some ions fly better than others. So all detected signals must be charged, and they're arranged by the mass over charge ratio, MZ ratio. Okay. Now this is example of a typical mass spectrum here for aspirin, right? Blood thinning painkiller. You see that this is the highest peak here, right? Your relative abundance right here is 100. So because you have at least one peak which is 100, that's the most abundant compared to the rest. So again, it's relative. Okay, relative. That's what's 100%. So this MZ value of 120 is for the singly charged ion, okay, in this mass there. Now, how do we find the resolutions and resolving power? So how much, right, we can separate the ions, right, in the mass spectrometer is described by the term called resolution. Capital R here, just like, in the previous case of CE, resolution is very important, is equals to M over delta M. So where M is the ion mass and delta M is the difference in the mass between the two resolvable peaks in the spectrum. Okay, so for instance, right, if you have an ion of ME value or MZ value of 100.0, right, and the other ion, the next peak is 100.1, right, you have these two signals, then the resolution is 1000 because the difference is 0.1, right, and then you have your 100 over 0.1 is 1000. So this is some mass spectrum we see in the past, not even in my days as undergraduate, but in another generation. So when you print out, it's really like a triangle. Now you see more lines, right? But you need to understand that because of technology advancement, that's why collapse become lines. But in fact, in the past, it's always like a triangle. Now this delta M is, you can take from two instances. One is your delta M is 50% height, the half width, right? Or you can take it like 5% height. You might ask why 5%? Because the base could have some noise. You can't be sure which is line, so you take 5% above it. Then this is the delta M. If you have two peaks that overlap here, so therefore you need to take at 50% height. So you can be sure that they are distinct signals. Two peaks resolve in 10% value over here. That means you cannot use the delta M at 5%. So you see it's safest to use 50% height. Okay. Now, in the resolution in mass spec, right? So here we contrast the QTOF, the quadruple time of flight mass spectrometry here. Quadruple time of flight, okay? Very high mass resolution. See the peaks are very narrow here. There's almost no overlapping, even for such a high molecular weight here. This is very good for untargeted screening for your identification. That means it's like a throughput screening. Okay, just scan what is it. I have some unknown here. Okay, I don't want to break it down to smaller pieces. Wait, what does it contain? Now contrasting the other one, which is your triple quadruple. So your TQMS, or you call it QQQ or QQ, right? It's very good for target analysis, for quantification, because once you have screened the sample, you know what is it. We go to the library and then we see how much of this sample you have inside. So it's it doesn't matter now whether we can see distinct peaks because we have known the structure. So now the question is no longer, what structure? I'm going to piece the information together, but okay, I know what I'm going to get my hands into here. How much do we have? Which means this also means that the demerits is low mass resolution, but we don't need that. So coming to instrumentation, now in general, you have the mass spec consists of ion source, the source of producing ions, a mass selective analyzer, and then of course an ion detector. So because mass spec, right, they create this gaseous ion phase, you need to have high vacuum. If you have no vacuum, let's say air, it just collapse and the ions can react together and don't get the ions you want. So it must be high vacuum, right? If not, you stick to the surface. So how do you manage it? We also have the magnetic sector, the quadruple time of flight designs to extract and accelerate ion optics for the transfer ions from a source to mass analyzer. Because ions are very reactive. They're so light. How do we sustain them, in the vacuum so that they don't shoot very fast and go to one side and hit somewhere else, not the analyzer. We have to sustain them time of flight and to create a kind of space for them, right, to fly. So in the vacuum ionizations, we have got the solvent elimination, right? Get rid of the solvent because solvent are source of also contaminants, and it will just cloud the mass spectra. Now, so in vacuum ionization, see that the solvent elimination and ionization step may be separate. So therefore, we use something called the Electron Impact ionization. The other one is called API, it's atmospheric pressure ionization. The solvent elimination and ionization step are combined into one single piece, at the source and take place at the atmospheric pressure. So we see the main difference is we must have high vacuum for sure, but what does it include and preclude? In vacuum ionization, the high vacuum is containing the ion source of the ions generated in the vacuum, analyze the mass and detect it. But the interface of the sample to the vacuum is outside. In API, you see that because it's atmosphere pressure, you ionize outside the high vacuum, but then once you have the ionized vacuum, you go into your MS there, right, to analyze the mass and then the detector. So note this difference between the two. Now, how do you create that vacuum? You can associate with your knowledge in your level 1000, 2000, even 3000 lab in the synthesis lab. Remember, to apply the Bushnell funnel, you need to have some suction, right? The pump or the rotary evaporator, you need to have some pump, but these are what we call the rotary pump. The pump is not that strong because it just rotate and spin, and therefore create some kind of vacuum. You also remember in your column chromatography where you need to pump the water to the Liebig condenser or the Graham condenser. The kind of pump is simple pump. Again, just to spin, right? And then you create some kind of a gap in air, and then just using the pressure difference to create a little vacuum. But this kind of vacuum is not sustainable in a mass spectrometer. So you need to create something called a high vacuum, and to do that you need a turbo molecular pump. You see, so many wheels to spin and gear, just more complex, of metals and expensive. The schematic of this spectrometer is okay. So for generation of high vacuum system here, right, rotary pumps are not sufficient. Right, you need to have super turbo pumps. Now this is important for the ion source. This is what we want to pay attention to, right? Terms like MALDI, ESI, ion spray, FAB, FAB, LS, IMS, EI, CI. These are terms you should be very conversant after this class. So first up is your basic ionization technique. Okay, note the ABCDs here. Your A is spray ionization, SI. Now, spray means, right, okay, you inject through a very little orifice. Because of the pressure difference, you like to separate it, right, due to the surface tension. Putting together is very tight, so you want to separate into all these aerosol. For B is DI, called desorption ionization. So you have a sample on the surface, and then your energy beam shoots it, and then it causes it to desorb and to escape from there. C is chemical ionization. So you have your substrate, and then you put in maybe H plus ions combined to form a charged species. And D is your EI, electron ionization, where you bombard electrons through it, or you shoot it, and then you shoot out electron to make it positively charged. Okay, or in this case, you have something like a photoelectric effect, similar, photons, and then you just shoot out electrons. You bombard it out, or you take one with you. So how do we describe this different ionization method here? So your EI is a hard method, electron impact. Okay, hard because, right, just come bombarding, very, very impactful. And this is good for small molecules about under 1000 Dalton. Because when we bombard it, right, we create different fragments, too many fragments there. So with this kind of jigsaw puzzle, we can piece them together to find a structure. And this is not good for large molecules, as you can see, because, right, like I mentioned earlier, when you keep on breaking all the different bonds there, it's just too complex. I have too much information, too much, and you can't piece them accurately. So next is your FAB, your FAB, fast atom bombardment, which is middle, intermediate, semi-hard. It's used for peptide or sugar molecules up to 6000 Dalton. Next is your ESI, electrospray ionization. It's a soft method now, used for bigger proteins up to 200,000 Dalton. So you still ionize it, but then it's soft. Soft, that means I don't want to cut all the different bonds, but it's a bit, those weaker bonds can get fragmented. So you don't have like so many atoms, but more of more fragments instead, short fragments. And the last one, which is more popular because it's more advanced technology, the matrix assisted laser desorption. Okay, ionization, your MALDI. MALDI is very soft. Peptide, proteins, DNA, again big biological molecules, and up to 500 kilodalton. So of course this is the best because it's not so hard, but it's soft, right? So I soft chop it, you can get it. But for small molecules, I'm not sure whether MALDI is good, because when you're so gentle, then small molecules, I need to fragment it to get some data. For, again, electron impact ionization, so how does it work? So sample introduced to instrument by heating, okay? You have a phase transition, okay? Liquid to gas, vaporize. And then the gas phase, right, these are bombarded with electrons. Coming from a rhenium, a D block element, or a tungsten filament, okay, shooting energy, 70 electron volt. And then the molecule is being shattered, cut, but shattered into fragments, because the bonds are actually electrons, right? So you bombard with electron, it weakens the bond, and then it fragments it. Okay. Now some perspective, your covalent bond normally like 2 electron volt to 5 electron volt bond, so of course 70 electron volts, more than that. Breaks it up, and then the fragments are sent to the mass analyzer. For EI, Electron impact here, the source uses the electron beam, okay, E-beam. Usually coming from this, tungsten filament like the one in some older light bulbs, okay? Again, purpose. Change it to a gas phase, either from atoms or molecules, right? And then also electron, take away the electron. You see? I use electron to heat up electrons. So you can see the ions, right, is always positive. Again, the schematic diagram here, you see you have a source of voltage, bombarding electrons there. And then once you generate the ions, you need to accelerate it and then detect it to the analyzer. Another diagram. Okay, so you have the inner of the gas sample where you vaporize it and then you ionize it and then shoot it out to the analyzer. Okay, you have this Planck's constant, back to your physical chemistry to calculate the electron energy, right? Because it's associated with wavelength.